In this video, we're going to explore how we can use enzyme kinetic data to determine exactly what our Km and our Vmax are. We've said in the past that the most important equation for enzyme kinetics is the Michaelis-Menten equation, which is Vmax times the concentration of substrates divided by Km plus the concentration of substrates. So what we're going to think about now is taking actual experimental data and determining Vmax and Km. So let's consider an experiment where you've determined the rate of a reaction with a variety of different substrate concentrations, right? So we're going to have this table of concentration of substrates versus experimentally determined V naughts. So our substrate concentration is all in micromolar, and our V naught is all in micromolar per second. So these are values that you will be given because you have determined them in an experiment in lab. Okay, so here's our values. So our goal then is to take these values and determine exactly what Km and Vmax are. Okay, and as we talked about in the past, you can take this data and you can plot the substrate concentration versus the initial velocity, and you'll end up with this profile that we've thought about before, right? So this profile is plotting the substrate concentration versus your velocity, and you end up with this, this curve shape where we can approximate Km and Vmax, right? So from plotting this, we might estimate that Vmax is, let's say, around 170, right? So we might estimate Vmax to be equal to 170 micromolar per second. And then from this, we can take Vmax divided by 2. So this is going to be down at about 85. All right, this is Vmax over 2. And we can trace this over to our data. We can see about this point maybe then that we can determine what our Km is. Right, so from this we might estimate that Km is about, let's say, 8 micromolar. So our big question then is this right? We are basing our Km value on an approximation of Vmax from this graph. And that's the big emphasis here, is we are approximating these values. These are not quantitative values. So what we want to be able to do is take this experimental data and plot it in a way where we can get truly quantitative experimental values for Km and Vmax. We cannot use this relationship that we have here because it's nonlinear and we don't have a good way of determining exactly what Km and Vmax are. Okay, so the approach we're going to take to this is we're going to take the inverse of both sides. So we're going to flip both sides, and we're going to end up with 1 over V naught. So we end up with Km divided by Vmax times the substrate concentration plus the concentration of substrate divided by Vmax times the concentration of substrate. And this simplifies to 1 over V naught equals Km divided by Vmax times 1 over the concentration of substrate plus 1 over Vmax. So the reason this is so very useful is that we end up with a y equals mx plus b situation. So we end up with a linear relationship where y is 1 over V naught, x is 1 over the substrate concentration, the y-intercept is 1 over Vmax, and the slope of the line is Km divided by Vmax. So if we plot 1 divided by the substrate concentration versus 1 divided by our velocities, we can get a straight line that has a slope to Km divided by Vmax, and the y-intercept, if that's the y-axis there, the y-intercept is 1 over Vmax. So we can use the y-intercept to determine Vmax, and we can determine the slope to determine Km. So let's try this. So I went ahead and plotted the inverse of all of these values. Okay, so we'll go ahead and scroll down here. And what we see is this really nice linear relationship where we have y equals mx plus b plotted. If you don't know how to do these plots, there will be a subsequent video that walks you through how to do these. But in this case, we have our slope, m equals 0.06, and our y-intercept equals 0.004. As we saw above, the y-intercept equals 1 over v max. So if we invert 0.004, that'll give us our v max. So v max equals 1 divided by 0.004, and this ends up being 250, and the unit here is micromolar per second. So we now have our v max exactly. We can determine Km because we know the slope, so m is 0.06, and this equals Km divided by v max. We know our v max, we know our slope, so we can solve for Km. So Km divided by 250. So here Km is 0.06 times 250, which is equal to 15, and our unit here is micromolar. So we can use these Lineweaver-Burk plots to allow us to use experimental data and quantitatively determine what Km and Vmax are. This approach is superior to using a direct plot of the velocity of the reaction versus the concentration of substrate, because in this case we have to guess what our Vmax is. And in this case we guessed wrong. And since we guessed wrong, that makes our Km wrong as well. So this Lineweaver-Burk plot is taking 1 divided by the velocity and plotting that against 1 divided by the substrate concentration.